conference in the tropics. So the first time, I'm still like a student in this subject. And then the first time Andy got me hooked, really interested on this three-cloud modeling problem, then, I tried to make some contribution in this field. So this is a joint work with Andy, as you see in the title of the talk. So basically, the goal of this talk is like, I'll try to convince you like what we are trying to do is basically we try to develop an efficient algorithm as well as provide some systematic guidelines to filter moisture-coupled tropical waves. So if I happen to meet that goal by the end of the talk, then I'm happy. So here, by filtering, what really mean is just a recursive algorithm for state estimation given partial observation. So this has been touched a couple of times. First, there's a first part of the introductory talk by Nejelka is actually give you quite a nice introductory. So, but here in the probabilistic sense, you can think about it this way. So basically, filtering proceeds as the following. Suppose you are given like data discrete time. At discrete time, let's call the data is Vn. That could be like any measurement. Then you basically apply this Bayes theorem to estimate what is the posterior estimate of U, that is your field of interest, given all of the observations from the past up to time n. So I'll just use that index. So basically what we are doing in the analysis step is you try to apply Bayesian theorem that is taking a product between your prior estimate here from any model that you believe, that satisfy the dynamical system, on the underlying dynamical system, and then you take that product with a likelihood function that is given by the observations, which is essentially just a probability of what is the observations given some truth that you don't know. Okay? And then, once you get this posterior estimate, you compute the prior distribution, and you basically plot some density of this to some model that you believe to come up with the next prior distribution. So there's a cyclic of forecast analysis. You just keep doing that on the fly. Okay? So the first point is, this is already pointed out in Andy's lecture yesterday, basically. So if all this density are Gaussian, and then all this model F here, as well as your likelihood observations model are all Gaussian, then one obtains the famous linear Kalman filter. So there's really, seems to be nothing to talk about, right? But the issue here is like, one issue at least, for high-dimensional nonlinear dynamical problem with multi-scale structure, as all of this tropical problem that comes up as the theme of this meeting, is that the computational burden essentially is in this forecasting step here. Okay, so imagine you want to make a forecast using a model that has a state of 10 to the 9th. So basically, not just to get the forecast, but this is what we are talking about is you want to try to make a propagation of statistics, right? Imagine if you need to forecast like covariance matrix, that's 10 to the 9 times 10 to the 9. You try to compute it like, so that could be an issue. So the real bottleneck is essentially here, okay? So here is the slides that I typically show the, applied mathematician, like why I have to convince them like tropical problem is essential. But here I'm sure it's very easy to convince you why it is. So one of the paper that I like actually a lot is from this bulletin of WMO. Mitch was here, but he's out. I'm sure he's happy looking at this. Basically, he reported that the difficulties in improving weather and climate prediction from days to years is just essentially due to the limited representation in the tropical convections and its multi-scale organizations in the current contemporary convection parameterization of the GCM. Okay, so that's one of the motivation. But we've seen over and over it's been spliced very detailed when Mitch actually give his own talk on that. Right, there's a mesoscale convection argument that he tried to argue. So then the second thing is that we have basically at the moment, this is also another point that's been pointed out by Nejelka yesterday. It's like we have a relatively accurate, data simulation scheme, that is prediction scheme for mid-latitude weather dynamics. Okay, so they are so good. Like all of this data simulation scheme works so well in the mid-latitude, so that it's really hard to beat in mid-latitude regime. So why is it so difficult in the tropics, right? I mean, Nejelka gave the point, but here, this is just a brief, what I think, you know, in my sense is basically, in mid-latitude, you have this geostrophic balance. So you know, all of the, all you care is like some perturbation around the geostrophic balance here. Whereas in the tropics, the Coriolis force vanish, and the dominant motion is basically vertical convection motion that is locally interacting with the large scale. Okay, and because of the Coriolis force vanishing, then you emanate a bunch of different kind of mode, you know, including the Kelvin, mixed Rossby. This is all these things that you guys are very familiar with. So it has some more complicated interaction relative to in the mid-latitude, which is pretty much dominated by Rossby and inertial gravity waves, right? On the other hand, in terms of data assimilation as well, we have like sparse velocity measurement. This is pointed out in Nejelka's paper in 2004 as well, you know, why we need this velocity measurement, but we don't have it because we don't have that many buoys or weather balloon, right? And what we have in the tropics, more or less now, is probably you need to use satellite data. But from the satellite data, what you can infer, this is what I learned, is that pretty much is the vertical column of the temperature profile, as well as probably just humidity. So you don't really infer velocity from the satellite data, which is a bit hard to do. Yes?
I have one question on this. That if you look at mid-latitude,
Okay.
ability of the models to predict in summer is very, I would say, less compared to during winter period.
Less compared to?
During summer, they are less successful
Okay.
compared to during winter period.
Okay. Okay.
During summer, what characterizes you have a weaker temperature gradient.
Okay.
If the problem in tropics is because of weaker temperature gradient or you know, if you have stayed it all right, then it should be as successful during summer also, but that's not the case.
Okay.
You know, there are people here
So that's another piece of educational.
temperature gradient which don't give you any strong signal anywhere. You don't know that form of the convection.
Okay.
Is that the issue?
So
rainfall drives your circulation here, and that's not taken into care in most of the data simulation problems.
right.
Mid-latitude, the gradients are weaker, but I don't know if you sure. But I don't know if
I don't, from my own opinion, I'll give you my own opinion, that's not a central limiter in the difficulty. But the weak temperature gradient is more a manifestation of the fact we have so many east-west propagating gravity waves in the tropics. So it weakens the temperature gradient indirectly.
Yeah.
Temperature value is constant value. Yes, that's what I said. That's what I said.
Could it be that the moist convection
Sorry. Yes.
Gravity waves in areas there.
could it be that there's more dominant effect of moist convection in the tropics?
Of course.
Way more.
Of course.
Way more.
Of course.
Regarding
Of course. Like in the modeling.
moist convection and triggering it is greater.
Of course. Like, you know, all that
That's
issue.
the point of our talk.
Yeah, that's-
Demonstrate this on the toy model.
Yeah.
How hard it is to do
Yeah.
this.
So that's the point. All of what you guess is, you know, essentially what it is. But here, this is just to give a essential background, like sort of, you know, 101 like tropical meteorology in my head. Okay. So there are many more issues on this, and one of the points we want to address is exactly what you say. So essentially, what I'm trying to say is like there are model errors. Okay. In the tropics, that's make it really hard. And second is like we have sparser measurement in the tropics relative to the mid-latitude as well, because it's not that populated. It's oceanic region, like most of it geographically. Okay. So another slide that you've seen this now 3 times at least, maybe in Andy's talk, in your talk, right? So basically, typically I use this slide just to convince people like, here is the state of your observations. This is from OLR, you know, superimposed with all this dry dispersion relations that was explained carefully in Andy's first plenary lecture. And compared to one of the GCM model, which does well on the mid-latitude, it does poorly in the tropics. I mean, this is, of course, it's 2006, and you know there must be some improvement over this. But the point here is like the model is we have model errors, so that's one of the points. Okay, so Now, let me really go to the subject. Those are just motivation slides. And what happened here is I want to talk to you about what is our contribution in this in terms of data assimilation here. So what I told you in the beginning is like the difficulty on doing such a filtering method is actually the model is expensive, right? In the forecasting step, there's bottleneck there are computational bottleneck due to expensive model. Yet the model is giving you some crappy result like this. Okay, so what I really want you to take away is exactly this slide. Is instead of focusing on developing the analysis or correction step now, so we study here the effect of model errors, okay, in the prior forecasting for the filtering scheme. So what I really mean is the following. We ask whether can we obtain accurate filtering skill by committing model error. So this is sort of the theme that Andy was talking about, okay, with a surrogate prior statistics, P tilde. So essentially, mathematically or probabilistically, you can think about it this way. If this is your filtering problem, right, here is the density of posterior that you try to get. I'm just getting rid all these subs indices, whatever, just to make it simple. So basically, this is the filtering problem you want to do, but let's approximate this filtering problem with the...
I just want to understand what you say here. It seems to me that the statement which you make here is a recognition or an assertion that the truth contained in the statistics is not in the model.
Yeah, that's true.
That's exactly. So you're not really, from that point of view, committing judicious model errors.
Well, we
compensating for those errors.
We are trying. Yeah, we are trying to compensate that model errors, right? Yeah, that's another way of saying. So basically, the main point is essentially we want to try to construct a surrogate statistics replacing this, right? Because we don't know it, right? In a sense. So well, if I want to try to construct this, then it has to be. It depends on some parameters that you got to learn from data set offline, right? So that's where the lambda is basically. So that's the approximate point. Then the main questions becomes like, how do you choose this P tilde, right? How to parameterize this lambda once you're certain, like, I want to use this particular model to get the surrogate statistics, right? And then third is like, how do you justify whether your choice is optimal? You have to have an unambiguous setting. You cannot, just throw in every single model errors into it and then say, oh, this is because of that. No. So that in this sense, like, we need a reasonable test model for tropical atmospheric dynamics, and this is where the three-cloud model really coming in. And the matter of how to choose P tilde here, with Andy, we have a whole book describing so many methods on this, okay, how to at least choose a reasonable P tilde. And then in recent papers, also I have a couple of other methods, as well as we have superparameterization that you mentioned. MQG could also be, that's in your second theme of your talk. So there are all these zoos of gazillion method, to estimate UQ. Yeah, these are all new method. So that can be used for data assimilation. So all of them are following under the same umbrella here, basically. So for this particular talk, I'm going to take the worst model that we have, okay, just to use it, and then we'll explain what we can explain, okay? So it might look funky to you. So to do this, first, like I said, we're going to use three-cloud model as a test model, okay? So Bulam and Andy created this model, 2006 and 2007, so I cribbed this picture from you. So basically, there's not much to say now. This is, because it seems like, this has been the theme over and over. So basically, the point is like, one point that I want to make is like, I also use the inaugural version of this model, which is the deterministic version, not the stochastic version. Later on, we can, of course, upgrade the model however you want it. So basically, I just use the worst, not the worst, sorry. The primitive, sorry, no, the primitive version of this model, okay? And that contains this three-cloud model. Okay, so I have to be a bit careful. Okay. So, in the paper that we work for this model, right, there are two kind of dynamics that we give out example. One is the MJO type, like a traveling waves. The other is the tropical weather wave example. So for this talk, I'll just emphasize on the first one, but the second one on the tropical wave example is actually very relevant to what Nejelka was talking about yesterday. So having said that, basically I took this 3-cloud model and applied the parameterizations in this particular paper by Majda, Steckman, and Khouider, 2007, where basically you choose all the time scale so that you get the traveling wave that looks like an MJO. So that's why they call it an MJO-analogue model. So basically, here is sort of a solution of the model. This is going to be my truth, okay? So we are playing God. This is the truth, okay? There are nothing about real observations or anything. So what solutions of this, I'm just taking these snapshots here. This is a space of 40,000 space kilometer snapshot, and here's the time that's going upward. What you see is that there are all this traveling wave 5 meters per second that going westerly on planetary scale. Together with that, there are all these intermittent small scale, mesoscale, basically westward propagating deep convection event that a lot of time they just die out in the envelope of this large scale waves. Okay. So here's one of the solution. And then if you look at moving average about this line here, about this 5 millimeter per second, and then I construct the vertical scale of the vertical profile of this model solution, then you can see all this very famous vertical tilting where you have low-level moist convergence and you have all these convections going on here, right? So here, the point of mine picking this picture is just for an example, like, look, this is what happened in one of the observations. It doesn't mean this is, there may be probably a lot of example that is exactly relevant, but the point is like this toy model gives you such a signature. It creates all the signature that look like MJO. Okay, so this is the nature. So now, I'm going to talk about the worst model that I was talking about for filtering, right? So the idea is like, here, how do we choose this surrogate statistics? So you can think of it this way. So suppose you have a dynamical systems here. What I mean is, you can think this could be a PDE, and you would be, a variable of your interest, okay? Then it might have some, linear dynamics. It might have some nonlinearity. This is just for simplicity. And you can think of it, it's I'm just resolving this PDE on a periodic domain for simplicity. But as abstract as this is, you can generalize it for more problem. Okay? So here, motivated by a turbulent closure approach, which was being used by many people in the past, that is by Dosol, Andy, and Timofeyev also used this for low frequency variability, etc. There's for FDT, like fluctuation dissipation theory application. There are a lot of different application has been used. But now, what we consider as our worst model is the following. We call it mean stochastic model. You can look at chapter 12 of my book with Andy, on how to really construct this. Basically, it's the following. Let's change the nonlinearity here, okay, by damping and noise. That exactly is the turbulent closure approach that has been applied anywhere else. Okay, the way we do it is basically, we here for this particular example, we're going to do this on Fourier modes. So you can imagine this is a bad model to do a forecast, right? Because now, once you do this, I basically get rid of all the interaction between different modes, right? Get rid of all this nonlinear interaction between modes. But why is this model, the motivation, I think, is that this you want to use noise, stochastic noise, to represent this nonlinear interaction just as a proxy. But then you also need a damping to make sure this model does not blow up in finite time, right? With this damping and noise, then you basically, on each Fourier mode, you are going to have marginal equilibrium distribution. So you will never blow up in the sense. Then basically the task is we basically parameterize this lambda here associated. That lambda is now complex value. It has some damping, it has some frequency, as well as the amplitude here, sigma, by fitting it to the exactly statistical solution. So you'll train this data using, you'll train this model using offline shelf data, right? And then you use this model to do prior for data assimilation. So that's the whole main point here. Okay? By doing this, then we avoid using the true model that could be really expensive because this is freaking cheap, right? Okay? Now, how do we do this in our context here? In this three-cloud model, they have like 8 prognostic variables. There are first 2 baroclinic mode of wind, potential temperature, and theta EB just represent the the boundary layer cloud. And then you have vertically average moisture. You have stratiform heating and convective heating. So it's 8 dimensional variable here. Now, let's try to do this, on this model. Basically, first, let's consider linearized multi-cloud model about the radiative convective equilibrium. So this is following the standard applied math techniques. That is, if you want to analyze linear stability, you linearize it about an equilibrium state, and we choose radiative convective equilibrium, which actually has been done in your paper, right? Yeah, you did it.
Equilibrium state being just a solution for d psi equals 0.
The solution that basically you want to match the radiative and convective to the equilibrium, right? Yeah. And then linearize, right? So here, in this sense, phi prime here, so this denotes just a perturbation field about this equilibrium state. And here, p tilde, I basically just denote some a linearized differential operator of this multi-cloud model at RCE. Okay? Now, let's consider a spatial discretization. So here I'm choosing such a coarse mesh, 2,000 kilometer, because in my setting later, I will observe only every 2,000 kilometer over the whole entire globe of 40,000 kilometers. So essentially, I only have like 21 observations, 20 or 21, right? So that basically, if you take a Fourier expansion on this, you can write it down this way, where this is the Fourier mode that I have. So omega k here is just a 8 by 8 matrix of eigenvalues of this operator. Okay? So then, basically, or this is what I just said, basically, okay, hold on. And now, let's consider another eigenvalue decomposition, because this is 8 by 8 matrix now. Let's basically diagonalize them, okay? So I'm going to diagonalize this eigenfunction here. And let's define phi as the following. So you can think of zk is, each column of zk is basically just an eigenfunction of this 8 by 8 matrix omega k that diagonalize this matrix, okay, in the Fourier modes. So that I can basically rewrite my whole systems in the diagonal coordinate, right? Now, so that's the idea is like, you linearize here. This is the turbulent closure issue. Add the damping, the forcing, and the noise, and then you fit them, right? You fit them to the statistics. That's exactly the general framework I talked about earlier, okay? So here it is. Then basically what we'd like to parameterize is the following equation, okay? So this is in the diagonalized coordinate. You want to parameterize this damping coefficient. You want to parameterize this frequency phase here, and then your forcing as well as stochastic noise. So where sigma k is basically related to this eigenfunction in the Fourier modes by this projection. So what we did is basically you just apply a regression fitting to the climatological statistical solution. So basically, as Andy mentioned yesterday, normally we can, let's say, compute some energy, like at equilibrium state, as well as correlation time decay. This linear stochastic differential equation has exact solution. So you can fit them, just solve that, okay? So in our work, we basically compute the statistics from the solutions of the full model, where that's the nature, right? at 40 kilometers. So you think of that's your nature. Then you basically apply your discrete Kalman filtering problem with this mean stochastic model here as the prior model. So here I'm basically just writing the model as discretized version of that, as well as this is the observations. So I'm going to describe the observations at the moment. I'm sorry for torturing you with all equations here. So, but the point that I want to make here is that the model here, the covariance of this model, this is basically it has eta. This is stochastic noise covariant. It has analytic solution that looks like this, okay, which depends on the coefficient from your fitting. And we are going to play with different kind of fitting here, okay, to create, let's say, a moist background covariance as well as a dry background covariance. So this is sort of like model error Q matrix in the standard filtering assimilation community, okay? So here we are going to derive an analog of 3D VAR. So basically what 3D VAR is doing, you can think of it, or some people call it optimal interpolation. It's like they're running Kalman filter, except they fix the covariance matrix B to be constant. And one way to choose it, this is a typical way to choose it, is that you choose this BK to be asymptotic of this covariance. So RB here, this is just a background covariance matrix. You took a climatological mean of that. And here, especially in our case, this is just a limit of this matrix QK, okay? Which is essentially just that. And Z and sigma K here are the coefficients arise from statistical fitting from the time series, whereas ZK are just the projection matrix that diagonalize between the eigenmodes, okay? So here, moist and dry background covariance B can be chosen appropriately, right? Based on parameterizations of sigma K here. So suppose if you want, a dry and cold model. So let's just fit, these 5 variables. So forget about the pretending that you don't have moisture as well as the heating, which normally you don't really observe anyway. So let's just fit let's just come up with a dry version of background covariance. The way to do it is you basically just simply replace this, where is it? You basically just replace this mapping here by this mapping where you shut off the other 3 variables. So basically, here is going to be your data, right? Now you fit it to this sigma using this to parameterize these things. And then you just plug in your parameterizations here to get your dry background. So if you want the full moist background, then you don't need this 5x5 matrix. That's pretty much it, right? One is moist background, one is dry covariance background. And this is also related to one of your Najelka talk as well. When she used the moist background, then it's actually working better, okay? Now, let me discuss the observations network. So we'll try to basically generate or try to play with this as close as to the observations. So in the sense...
John, just one comment. Operationally, people want to use a dry background, and one of our points is that a moist background is much better.
Okay. Yeah, I will make that point. And actually, in the slides that she's talking about yesterday, she generates a moist background, but she used the dry eigenmode.
That's what I do.
We use moist eigenmode to generate moist background.
My only comment is we know our own work.
Of course.
I'm trying to foreshadow for the audience.
Of course.
That
Of course.
This is what people are doing, right?
Of course. Of course.
We
So,
don't advocate that.
so here is sort of a set of observations that we're going to play with. Is we are going to pretend we only have, let's say, surface observations. That means you only have wind, potential temperature, surface height, and so on. So this is what I'm talking about, is the online observations on the fly. This is what we have, okay? As well as you can add middle troposphere temperature, about 8 kilometers. You can also add mid-troposphere temperature as well as velocity at 8 kilometers. Of course, for diagnostic purpose, since we want to make a comparison, you can also pretend you observe everything, which is probably not the same as in reality. But, to check all of this. So here is a first result that I want to point out. Here, let's say if we just take surface observations, okay? So what I'm showing you here, this is a lot of figure. It's basically the average or moving average profile of the first baroclinic mode velocity, second baroclinic mode velocity, potential temperature, first, second mode, the boundary cloud layer that we observe, the Q, which is vertically average humidity, as well as the heating content, and this is the precipitation. So the first things, this is quite depressing, and we want to explain this, is like, here's the precipitation. Look at some of the scheme here. The true precipitation is basically given by this dash. So that's the truth, okay? What we have is too much rain. This is insane rain rate, right? So why is that? Like, when you observe only surface observations, why is that? So this is, just to point out, this is an unrealistic estimate of precipitation, with this type of filtering approach, right? And with all of this approach that we're talking about, either you use dry background, you use moist background, there's a reason behind this. It's basically, let's look at the precipitation budget for this model. So for this particular model, you use a combination of Cape and Betz-Miller type parameterizations, right? So this is the precipitation budget. It's basically there are contribution from the boundary layer cloud, contribution from the vertically average humidity, as well as both baroclinic potential temperature. So if you look at all this carefully, right, basically the coefficient that we choose that match to your paper actually is the following. There are only small contribution from the boundary layer cloud, small contribution from the vertically average moisture, also small contribution from theta 2 here, which is the second mode, baroclinic mode of the potential temperature. But the first mode here is awfully large, So basically, here is the culprit, right, the theta 1. So it actually makes sense. So here you think about it, let's look at the profile of theta 1. So the truth is there. So there is a sensitivity. If we underestimate this potential temperature, you actually make a damage on this estimation of the precipitation. Okay, so we don't observe all these variables like the Q. We don't observe it. So the main message here for practitioner is like, if you really want to, do a correct data assimilation on precipitation, perhaps you should consider to build a measurement instrument to measure this, the mid-troposphere temperature. Okay. So second point here, this is exactly to our point, is okay. Now let's consider just surface observations plus mid-troposphere temperature and velocity. Let's assume we have these observations. So what I show you, instead of 9 figures to torture your eyes, now I'm just picking the 3, okay? So this is theta 1, that is the essential key ingredient here. So because we have mid-troposphere temperature, then they're good. So this is observed variable on the fly. This is unobserved variable, okay? So this is humidity, and this is precipitation. Now, in each of this subplot here, I have a couple of schemes. Basically, the truth is just the dash gray dash, and then here's a posterior estimate with moist background that is in circle, with dry background that is in diamond. So let's just pay attention here. So here is your estimate on the precipitation. If you use a dry background, okay, so this is what you estimate. It's actually you completely miss the true precipitation profile here that is estimated by the moist background. So it is essential to include, from this exercise, academical exercise, then the message is it is essential actually to generate a background covariance that is moist, right? As this is also confirming with the recent result by Nejelka yesterday. Okay, so now let's look at some of the vertical profile that we obtained by this technique actually. So whatever that I show you on the left, these are the truth. Okay, so each of these are basically, you can think of super ensemble average of the solution. Okay, so or climatology. Okay, So the first one here, this is just potential temperature. As you see here, it's a low-level convergence. This is a velocity vector on Z and 40,000 kilometer. Here's where the deep convection heating, and this is just the horizontal velocity. So whatever that I show you on the right, this is the posterior estimate from the filtering strategy, observing surface observations and mid-troposphere temperature and velocity. So you can see they're doing fairly well with such a cheap model, right? Remember, I told you I used the worst model that someone could think of, right? So they're doing, no, actually they don't give me a nonsense. So it's pretty decent, right? So imagine then Andy has all this fancy method on development of the model. Then I have a very, very, very strong feeling. Then we're gonna claim victory pretty soon if it's really implemented. So now let's take away. So what I'm taking away is like mid-troposphere velocity. So I'm just taking it away. Let's see what happened. Well, you still get the potential temperature contour, but the signature here, this vertical tilting on the wind, it's just gone, barely. You don't see all this tilting anymore, right? Now let's also take away the mid-troposphere temperature. Here's just the surface observations, right? So what you get is it's even worse. You don't even get the convective heating parameterization. So I was actually a little bit interested when I hear one of the talk in the second day when they say sometimes we get rain, sometimes we don't. And they were analyzing this weather data. Actually, it's NSAP product, right? So is this maybe the case? I don't know, but I'm thinking, I'm just throwing an idea. Maybe there's something about the data assimilation scheme that they're doing, maybe not incorporate the correct observations. It's just a conjecture. I don't know. Okay, it's because I don't know what they're doing. Okay, so now here is another result here. How many minutes do I have? 5. Okay, so it should be fine. So basically, what I'm showing here, this is an error. So this is RMS error between the truth that I know, right, as well as the posterior estimate. So you take the RMS error, I plot it as a function of observation time interval. So, this is, I observe more frequently, and here I observe less frequently. This is all in hours, days, sorry. I observe every 2 days, 4 days, 6, and so on. And on each curve here, here is my climatological variance on the system, meaning, if you observe everything, let's say, okay, you want to do better than that, right? You want to do better, you want to have a better prediction than your climatological variance, right? Otherwise, why am I doing data assimilation? I just trust that, right? That's one thing. If you observe everything. And here is the level, here's a dash here, there's a dash. This is all my observations noise, the online observations error, okay? So I take them to be about having 10% variance of the climatology to make sense. Because if I make a measurement worse than climatology, what's the point of even using that observations, right? So you can see the error of some of these observable variables. They are all lie in between. Sometimes they are up there, and so on. But what's most striking is the following. Think about, look at this picture. Why in the world, when I observe less frequently, say here every 8 days or 6 days here, I got actually better result than I observe too frequently. It's quite amusing, actually. So basically, right? So that's what I want to make a point. So basically, you can use mathematical theory to understand this point. So for example here, the point here that I want to make is the following. There is something in the control theory or in the filtering, the old date filtering, that basically just say, if you want a convergent solution, you need something called observability condition, okay? So in this case, here I'm checking where I don't have full observability, where I only observe surface observations and mid-troposphere temperature. So I have sparse observation. So when delta t here is 6 hours, my eigenvalue of the model, okay, the largest eigenvalue of my model operator is almost 1, meaning they are, they are close to divergence. Actually, they are basically marginally stable, right? Whereas if I take it over 72 hours, they stabilize. So the eigenvalues is less than 1 here. Okay, so that means, yeah, there you go. The shorter time is marginally stable. So in this case, the observability condition that I say is actually necessary here is practically violated, because when I compute this observability condition for this matrix, when I have shorter time, what I found is they are 10 to the minus 20. Sure, they are not 0. Okay, the observability, so for those who probably got confused why I compute this, observability condition is basically saying like, if I take observations, if I take my dynamical system, project it on the observation space, right? Can I recover the can I represent my solution by all this measurement? So essentially, mathematically, you can think about it, whether can all this subspace, can all this solution, or observations in the observation space here, can it span the whole space of my solution? That's basically what it is. So that's why I compute the determinant of that matrix. Okay, when you compute it, well, they are not 0, but they are practically nonsense, right? 10 to the minus 20. So that's explaining why you have such a behavior. So let me close my talk here. Yes?
It is doing a sort of plus empty.
Yes, sparse observation, right? So the summary here is like, as I told you, our test problem suggests that slight underestimation of mid-troposphere potential temperature will produce overly wet atmosphere. So I hope that's not what caused the monsoon. It's a different thing, okay? And this is unrealistically high precipitation rate. So second is that our reduced stochastic model can recover some moisture precipitation field profile, even when online observations of these variables are not available, provided only the filter prior model is designed with a moisture-coupled eigenmode basis. Okay? So a better estimate for the tropical wave pattern requires more than surface wind and potential temperature. And we show all this filtering skill, as well as I demonstrate the counterintuitive finding that, like, sometimes why we need to relax a bit to take the observations, not just keep taking it rapidly. So there's all this underlying principle. So for this whole talk, I am actually discussing this paper. So there, as I said, there's a second example that represent weather wave pattern. So the basic fundamental why we come up with all this idea in this paper, you can just read, many chapters in our book if you like. And for the model, basically I learned it from these two papers, obviously from the three of you, and then as well as the parameters that I use for running this model, I use this particular regime here that is an analog of MJO. With this, let me just close the talk. I'll stop here.
Thank you. Yeah, we can have a couple of quick questions.
Yeah.
Can you please go back one slide previous? Theta 1, what is the next one. Theta 1, what is the accuracy you need? The accuracy of that measurement. You said you have to measure theta 1 in the mid-troposphere, but with what accuracy?
With what accuracy?
Yes.
Okay, that's a good question. This is theta 1, right? This is when you take the precip. Actually, this is not a right slide. Actually, here, theta 1. Okay? The true theta 1 is like that. That's the dash, right? Okay? Just slight inaccuracy of theta 1. Look at that. That gives very slight. That's the circle is probably the next best one, right? This is just a crappy thing, right? The diamond and whatever, this is just a dot. So look at just the circle here. We have some slight underestimation of theta. And the circle is somewhere in here. You also already underestimate. So it's very sensitive. It's actually essential.
Because none of the commercially available radio sounds will do this. None of the commercially available radio sounds, they have this kind of accuracy. The answer is about 1K.
Let me comment.
So basically, the point that I'm trying to make is that, right? Okay,
I think two issues could easily be confused. We have in our multi-cloud model these three parameters, A1, A2, A0, and it so happens in the MJO-analogue. So this is roughly our deep convective. It's our deep convective precipitation in all versions of the model. For this particular version, to get a nice MJO-analogue, we needed A0, which we call the buoyancy frequency. We needed that very large. So one can be misled. So once A0 is very large, you're maybe exaggerating the effect of how important it is to get theta in a realistic model. For example, in the second part of our paper, where we studied the analog of a convectively coupled Kelvin wave, a weather wave developing into a convectively coupled Kelvin wave train, we had very different parameters, and this sensitivity is gone. So let's not confuse precipitation in nature with parameters in the model.
right.
And we don't want to do that. So let's be fair. Let's be fair. But we are struggling to get precipitation also in the other case when you look at the paper.
Yes.
And I just want to make another comment.
Yeah.
I view with great skepticism all the reanalysis products. So Mitch isn't here anymore, but Mitch is my good friend, and I would say it in front of Mitch, and he knows I would. I am very skeptical that in the Yahtzee data set, the reanalysis products for precip and critical variables of humidity are all that good, even at high resolution. Because I see, when I've seen talks on that, anomalies of 30 Kelvin in the boundary layer, which don't exist in nature from the reanalysis product in Yahtzee. Over ocean, over Central Pacific. And these are data assimilation artifacts of linear tangent modeling of deep convective events by things that don't respect moisture, the problems Najelka was talking about with ECMWF system. So I view with great skepticism for many purposes whether some of these products on the fine field variables are what they think they are, and at least our analysis points to that.
In defense.
No. I think Yahtzee is a very valuable thing. I'm not criticizing Yahtzee overall. I'm just...
In defense, I think Mitch may say so, so he's gone, so let me tell it.
I know, this is easy.
I think the biggest advantage of Yahtzee would be not necessarily to use it as a tool, as a data set to be analyzed further, but let's say to be used in other kind of simulations. For example, for the regional climate model that you may need boundary conditions of the larger areas, which assimilations of those additional data sets doing Yahtzee is good.
I'm criticizing the literal interpretation of some of the data in Yahtzee. I'm not criticizing its value for other things. I think it has great value.
Okay. Let us thank the speaker. Maybe we are slightly behind.